Hey everyone, what we're looking at today is non-uniform charge densities for different charged objects that are insulators. Insulators have charges that can be all the way through the material. If it was a conductor, charges will be on the surface of the conductor and we won't have to worry about the insides. If you look at the problem here, this is problem 43. In problem 43, we are solving for the total charge on this sphere. The density you can see is written as B over R. And they want to know what the electric field strength is on the inside of this insulator, as well as the electric field strength outside the insulator. So let's start with the first thing. Let's find the total charge. So you can see what we have here is that rho is B over R, and we know that rho is a charge density of charge per unit volume. So if I want to solve for charge, I can just take it as rho multiplied by the volume. But here's the thing with this. What this density is telling me this time is that the density is not constant. The density is decreasing as we get further away from the sphere. So if this is my sphere here, there are many charges packed in to the center here. As we get further and further out, the density of the charges is going to die off by 1 over r. So by the edge of the sphere, when we finally get to the radius r, then we are fully outside the sphere and all the charge is contained to that. That's what we're dealing with. So let's do this. You can't just do rho times volume, because you have to add up every single amount of charge for every single volume of the sphere you make, whether the volume is very small or if the volume is the entire sphere. So we're going to have to alter this just a little bit and solve for dq throughout the dV, throughout all the different volumes that we can integrate to. If we remember volume for spheres is 4/3 pi r cubed. And if we want to get dV, that means I have to take the derivative of the volume equation. And the derivative gives me 4 pi r squared dr. So I'm going to put that in for dV here. And when I do that, I get dq b over r 4 pi r squared dr. And when I look at my bounds for integration, I'm going to go from no charge to having all the charge on the sphere. And if you look over here, when I do my integration on this side, I'm going to go from no radius until I reach the outer radius, big R. So let's pull out the constants of that integration and see what we get. dq is an easy one. dq just becomes q. So I'm going to pull out a b, I'm going to pull out 4 and a pi. I did have r on the bottom, but I also had an r squared up top, so it eliminates one of my r's and leaves me just r dr. So if I integrate r dr, that's going to give me r squared over 2, and I have to evaluate that between my two bounds of 0 and the big radius. 0 is easy. I put 0 in there, it's going to knock out that whole equation, so I just have to put in big R. So the charge that I have is going to be b 4 pi big R squared over 2. But we can do one more simplification. I can get rid of the 2 and the 4 and be left with that. So b is a constant, 2 is a constant, pi is a constant, and r is the radius of our sphere. So the total charge on the sphere is this equation. What we want to do now is look at our sphere that has many charges here in the center, and then the charges again get spread out the further out we get. What we want to create is Gaussian surfaces inside and outside this sphere to calculate the electric field strength around each. Let's start with the inside. For the inside, I'm going to put a Gaussian sphere that is enclosing some but not all of the charge, and it is a certain r distance from the center. So the Gaussian sphere has a unique little r radius away from the center of the sphere. So if we use Gauss's law, we get E dot dA equals Q enclosed over epsilon 0. Again, the electric field is uniform around our Gaussian sphere, so we can just have electric field multiplied by the area. The area here is the area of my Gaussian surface, so that is 4 pi little r squared. And the charge enclosed now, I have to be careful. I haven't enclosed the entire amount of charge, so if I go back to my Q equation, it's going to be b 2 pi little r squared, because that's all the charge that I have enclosed up to this point. So now looking at our formula here, we can do some cancellation. We can knock out things that are on both sides of our formula. So I can get rid of the pi's, I can get rid of a 4, and just make that 2. The b is going to stay around, but if you look, I've got r squared on both sides. So I can actually eliminate r squareds, and the electric field inside this insulator ends up being b over 2 epsilon 0, which means that my electric field strength is constant inside the insulator. So I have a lot of charges near the center. The electric field is a certain strength, but as I encompass more and more charge, remember the density gets less and less, so the electric field actually stays a nice steady constant all the way until the radius. But now let's look what happens when it goes outside. When we make our Gaussian surface outside now, little r is the distance to our outer Gaussian surface. So we do this again and say the electric field is uniform out there. It's still going to be 4 pi little r squared for the surface area of our Gaussian sphere. And now the charge that I've closed up is actually all of the charge. So it's going to be that 2b pi and big R squared this time, all over epsilon 0. Not as much is going to cancel this time. The pi's still go away. The 4 and the 2 cancel out, which leaves behind the electric field outside the sphere is b r squared over 2 epsilon 0 little r squared. So if you look at the electric field outside, everything is constant except 1 over r squared, which means that we can treat the sphere as a point charge once we get outside the radius. So all things do look like point charges when you get far enough away, or if they're spherically shaped, we can treat them as point charge. But in terms of the charge density, you don't necessarily say it's kq over r squared. So this is the electric field outside. We calculate the electric field inside, nice and constant until you get to the radius, and then dies off. Let's try another example. So in 55, we have an infinitely long non-conducting solid cylinder, which means, again, we have an insulator with a non-uniform charge density. So the density varies with radius, and they give us that the density is b r squared, where b is just some constant. Part A wants us to prove that the linear charge density of this cylinder is pi b a to the 4th over 2, which means that we can't just write that as our answer and expect to get a point on the test. They've given you the final answer. You've got to use the knowledge that you have to get to that lambda. But if you don't get that lambda for part B, you can use it to solve for the electric field strength with radiuses inside the cylinder less than a, or radiuses outside the cylinder greater than a. Okay, so here we have our charged cylinder, and the cylinder, they want us to prove that lambda in the end needs to equal pi b a to the 4th over 2. So where are we going to start with this? Well, the first thing they told us was that the rho was little b r squared, which again means that our charge density is very thin in the middle and gets very thick as we get towards the outer wall. So if we want to solve for q, q is rho times v, and we have to add up all the charge from the inside of the cylinder to the outside of the cylinder. So it's going to be dq and dv. So this time we have to integrate the volume of a cylinder. Well, the volume of a cylinder is the area of that end cap, pi r squared, times L. So it's area times length. So dv would be then 2 pi r times the length, dr. So that's going to go in for dv. I have rho that I can put in here, and let's see what we get when we combine all of those. dq just becomes q. So pulling out our constants there, the 2, the pi, the b, the length of the cylinder, those were all constants. R cubed dr is what we have to integrate from 0 all the way to a. So from no radius all the way out to the radius of the cylinder. So r to the 3rd becomes a4 over 4 minus 0 for that, which just gives you 0 again. So we're going to multiply our solution here for the integration by all those constants. So q is 2 pi b L a to the fourth over 4. Which looks like we almost have the answer. The answer, remember, needs to be pi b a to the fourth over 2. There's nothing about length in there because we solved for charge on the cylinder. We didn't solve for the charge density. Since lambda is charge per length, I can take this q and divide by L. And if I divide by L, what I'm going to cross out is the lengths, and I'm going to cross out a 4 and a 2. So if we go back, we should see pi b a to the fourth over 2. That's what remains for our lambda, or our linear charge density. So now that we know our charge density, what we need to do is solve for the electric field inside and outside the cylinder. So we're going to make Gaussian surfaces again, and since we've got a line of charge, I would recommend a Gaussian cylinder that is inside and a Gaussian cylinder that is outside. We're going to do this for each. Remember that the electric field is, if this is positively charged, away in all directions. So we want to calculate the electric field out of the sides of the Gaussian walls. I don't need to worry about the end caps, I just need to worry about the sides. So we'll do E dot dA equals charge enclosed over epsilon 0. Okay, the electric field at any distance from the cylinder will be constant. So dA just becomes the area of the cylinder. So the side area of a cylinder is 2 pi r times the length equals the charge enclosed. Now the charge that I've closed up here is lambda L. I can use the linear charge density and the length, so I don't have to worry about just Q. And what that lets me do is eliminate the length. Remember that this L over here is the length of my Gaussian surface. I can make that Gaussian cylinder as long or short as I want. When I use the charge that I've enclosed, I've only enclosed the amount inside my surface. So that's why I can eliminate the L. The electric field here ends up being lambda over 2 pi r epsilon 0. And if you want to find the electric field, again, for outside the cylinder, well, that means I've enclosed every single charge present. So lambda, remember, was 2b a to the fourth all over 2. And we still have the pi, another 2 down there, so 2 times 2 is going to give us 4 r epsilon 0. So if we eliminate some things in there, the pi's will go away. 2 times 2 is going to give me 4. So there's our electric field outside the cylinder. You get b a to the fourth over 4 epsilon 0 r. Everything is constant there except the 1 over r relationship. So away from an infinite line of charge, we said that the electric field dies by an inverse relationship. Well, here it is, just with a bunch of different constants. But let's look at how the electric field is different on the inside. So the same thing applies when we have a Gaussian surface inside the cylinder. The 2 pi RL is the surface area of a cylinder, and lambda times length is the amount of charge we've closed up. But the only difference is, instead of doing lambda as pi b a to the fourth, because a is the full radius, we're just going to do r to the fourth over 2. And we're going to take that lambda over epsilon 0. On the other side here, I have electric field strength is 2 pi r times L. We've already eliminated the L because, remember, the L was our Gaussian surface. So things that I can eliminate will be pi's. The 2 and 2 are going to combine again and make 4. I can get rid of one of the r's and make this r cubed. So the electric field inside the cylinder is b r to the third over 4 epsilon 0. The only thing that's changing here is the radius, or the distance I am from the center of the cylinder. So it's going up as a cubic electric field strength on the way out of the cylinder, but once I get outside the cylinder, it's going to die off as 1 over r. So graphing electric field strength versus distance, when I get to a radius of a, I have a cubic growth on the inside and then a 1 over r relationship on the way out. Infinite line of charge is still true on the way out, but you can see because of the different charge densities on the way in, you're going to have to deal with including every single piece of the charge when you try to solve for your Q enclosed. You can try a few more examples from the back of the book. They have some more non-uniform charge distributions for cylinders, a couple more for spheres, but make sure you know how to do these so you can do well on your AP test.